Hello, linear algebra student. Now that you know the use of invertible matrix, especially the 2 by 2 one, we're going to know more about the facts of this invertible matrix. And later on, we'll talk about how do I find the inverse of a 3 by 3? Is there another formula? What about 4 by 4 matrix? Oh, and one thing that I didn't talk about is invertible matrix, or the inverse matrix is only available for a square matrix, mainly meaning n times n, because identity matrix is always a square matrix. So how can you have an identity matrix? Is if you have a square matrix, so A must be n times n. So if you have a matrix that's 2 times 3, 2 by 3, there's no inverse. Okay, so no matter how hard you try, it's not going to be a identity. So some more facts. Okay, so the first is if A is an invertible matrix, so implicitly that means A is a square matrix and A is invertible, then you can do the inverse of the A inverse and it will become A. Okay. Kind of like in numbers, so 5 inverse is 1/5, right? And 1/5 inverse is 5. It's just a circle. B, if A and B are n times n invertible matrix, you see how they are square matrix, and so is AB. So if two of them is invertible, if you multiply them, they're still invertible. And then the inverse of AB is the products of inverse of A and B, but in reverse order. So similar to the transpose situation. So if you multiply two inverse and you want to find the inverse, it's the same as you find the individual inverse, but multiply in a reverse order. C, if A is an invertible matrix, then A transpose must be invertible also. And the inverse of A transpose is the transpose of the A inverse. So kind of like if I have 1, 2, 3, 4, this is invertible because 4 minus 6 is right. So then A inverse so would be 1, 2, 3, 4 in a row in a column form from the row. This is still also invertible. So both are invertible. And also more about products of matrix, inverse of a product of matrix. So it's not just two. So if you have A times B times C inverse, you can also do it reverse way. So like three of them, it would be the product of the inverse of each matrix, but multiply in a reverse order. Okay, so it can generalize to more than two matrices. So we are moving into how to find 3 by 3 inverse. If I have an inverse that's 3 by 3, how do I go about finding it? There is no formula. Only the 2 by 2 has. So we would actually the method to do it is by a method called elementary row operations. Do you still remember elementary row operation? Like add a whole row of a matrix, and in the past it was augmented matrix, right? So that we can solve the equation. And then so the like add two row together or exchange two row or add the multiple of one row to the other row and replace the sum with the other row. So these three elementary row operation actually can be used to find the inverse. So what is it? So to begin with, we talk about something called elementary matrices. So there's three types of elementary matrix correspond to each elementary row operation. The first operation is the more complicated one. For example, I want to add row 4 times of row 1. So for example, if I want to do 4 times of row 1, actually negative 4 times of row 1, and I want to add to row 3 and replace row 3. So this is usually what we do if we want to clear some entries in row 3 to 0, right? Row 1 is our pivot row, and we do that. So what happened is, if I want to do that, I can do the same thing in the identity matrix. Remember, the identity matrix is for 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. So we can do it. If you do it, so you can see I multiply R1 by 4, so it'll be negative 4, 0, 0, and I add row 3, used to be 0, 0, 1, so now it becomes negative 4, 0, 1, right? And then A is supposed to be what? It's supposed to be ABC, no change, right? D, E, F, no change. What about G? This will become, adding 4 times of A will be G minus 4A. What about H? Will be H minus 4B. What about I? Will be I minus 4C, right? So this is what it's supposed to be. And it turns out that if I use whatever that I did in the identity matrix, then this would be called the elementary matrix. If I use this elementary matrix and multiply with the original one, you see that I actually get the same result as if I'm doing a row operation. So what do I do? So this would be a row times a column. So that would become A only. A row times a column, just an ABC, right? And then this row times this column, I only have D because I only have a 1 here. And then E, F. Now this row times this column would be negative 4A plus G. Exactly what we did if we do it manually. Actually, negative 4 row 1 plus row G. You can see if you multiply this elementary matrix to it, you're actually doing a elementary row operation. So negative 4B plus H, negative 4C plus I, right? So using whatever that you did for the identity matrix, using this elementary matrix to multiply for the original run, it is as if you are doing an elementary row operation. What about if I swap two matrices? If I rows, if I if I swap two rows, for example, row 1 and row 2, row 1 is ABC, DEF is supposed to be DEF and ABC. Now, if I do the swapping in the identity matrix, you can see that row 1 becomes 0, 1, 0, and row 2 become 1, 0, 0. I use this to multiply to ABC, and you will see that the result is the swapping of 1 and 2. This row multiplied the first column will be D. This row multiplied this column will be E. This row multiplied this column will be F. This second row multiplied by the first column will be A. You can see A, B, C. And then the last one is G, H, I. You can see that when I actually swap the identity matrix and then use this elementary matrix to multiply to the original matrix, is as if I'm swapping row 1 and row 2. So that means this matrix helped me to do the swapping. And then the third one would be sometimes we just multiply a row by a number, right? In this particular case, we say row 3 times 5, put it back into row 3. So I did it in the identity matrix. It become an elementary matrix. So this is elementary matrix. And I'm going to multiply to the original matrix to see if I get the same results as if I'm doing it. So row column, that is still A, this is still B, this is still C, right? Row column is still D, E, F because only the second one has 1. Then the last one will be row times column. It will be 5A, right? Oh no, 5 row times column, 5G. And then it will be 5H and 5I. You can see that it is actually 5 times of row 3, right? So if you want to do the elementary row operation of the original one, you use the elementary matrix and you can multiply it. So in a nutshell, you can see elementary operation. When an elementary operation is performed on a m times n matrix, the resulting matrix can be written as EA, where E is created by performing the same row operation on the identity matrix. So this elementary matrix E, they're all invertible. They're all invertible, and the inverse of E is the elementary matrix of the same type that transform E back to I. So the good things about this is when you are doing this, it's the same. The inverse of this is actually going back, right? Because they're elementary. These, I didn't go into detail, but you just have to trust it. So that means if you start off with a elementary matrix and you swap until it become the original matrix become elementary, then this will become the inverse. So this is the idea of it. So so this is the idea. The idea is if I have a matrix and it is n times n is invertible, then I'm going to do elementary row operation to the A augmented with I n. And I do the operation so that this become I n, and then this will become A inverse. And I'm doing elementary row operation. So go elementary operation. Because when I do this, it's invertible back to A. Yeah, so this is the algorithm. So let's try to figure out, do the elementary row operation and find I first, and then I'll come back to look at the elementary matrix. Oh yeah, well, let's wait. Right, let's do this first. I don't think I have time to do this, finish this within 15 minutes. So if I want to do 2 times of R1 plus R3, go back to R3, what should it be? So my I3 is 100010001. So to do this, my E would become what? I'm going to multiply this by 2 and add to row 3. Right? So row 1 stay the same, row 2 stay the same, but row 3 become 2 times of it, so I have 2, 0, 1. So what is the operation performed by this? So, this is should be 1. So it was originally a elementary matrix, but I multiplied 2 in the middle. That means 2 times R1 become 2 times R2, go back into R2, right? So that is the corresponding. So in the next video, I'm going to talk about how to switch, okay, by elementary row operation of this matrix 0, 1, 2, 1, 0, 3, 4, -3, 8. On this side, I'm going to have the identity matrix. Oops, 0, 1. Okay, so this is the identity matrix. So I will use all of our elementary row operation to switch this to I, and then at the same time when I'm doing the row operation, this will become A inverse. So watch the next video.